And so we'll go over, we'll talk a bit more about that stuff a bit later and send it out and everything. Okay, but I think we'll just start for now, and then as more people come in, they'll just come in later. Essentially, if you remember from last week, or not from last week, from a couple weeks ago and a couple weeks before that, how a neural network works, um, I think we talked about it a bit. Essentially, you have your input layer, which has a bunch of various input values. These are normally numbers, but they're technically sensors or variables, right? So if you remember that email spam example we had, where it's like to detect if an email was spam or not, you could have like these variables, features, and those kind of get entered into your input layer for your neural network. And then you have a couple weights, and these weights resemble the strength of the connection between your input layer or your input value and your hidden layers. And then you have a bunch of hidden layers, then you have an output layer. And today we're going to create a mini neural network in Python. It's not going to have that many hidden layers, but it will have a sigmoid function, which we'll kind of talk about a tiny bit. It's a bit advanced, even for high school level. And but we'll have an input layer and a working output layer. So start, this is my VS Code. Hopefully, I think everyone can see it. I'm going to create a new file called, I'll call it neural.net.py. Nice. And so the first thing we want to do is we want to import this. Oh, so if you're following along, that's totally fine. But if you're having issues following along, that's kind of normal. You can let me know, like put it in the chat or something. I'll try to help, but it might not work out. Import numpy as np. We have not ever gone over what import functions do, but essentially in Python there are a bunch of modules, and a module is essentially like, you can think of it like as a class or a bunch of functions and that someone else has already created out there. So let's say there's a module specifically for like plotting curves on a line, or there's a module specifically for doing math and addition, which is like a default module, by the way. And there might be a module specific for like a foreign language, right? Let's say you need to translate everything from English to Spanish, and there might just be a module for it. Stuff like that. Basically, NumPy is, um, I don't know what the best word for it is, but it's it's a Python module that's used for data science and machine learning and AI, and it's really good for working with arrays and matrices and like linear algebra, which is roughly the basis of our neural network. And we'll talk a bit more about that a bit later, which it might sound a bit confusing now, but it's honestly not as bad as it sounds. And so now let's create our class. We haven't really ever gone over classes before, but it's kind of self-explanatory a bit. Essentially, we're just encapsulating a bunch of functions within this neural network class. It'll make sense pretty soon. And then this is our first function. It's called init self. Essentially, it's to create your class object. You don't have to worry too much about the technicalities. Okay, so the first thing that we did, or that I just did, was np.random.seed1, and I'll explain what that means in a second. Essentially, np.random.seed1, it creates a random seed. A seed is, the best way I can explain it is like, it's like Minecraft. If you've ever played Minecraft, you know, you have a random seed every time you play for your world. It's basically the same idea. When you generate random numbers in NumPy or in Python, they're not actually random. They're like pseudo-random. What that means is that they're pre-generated randomly, and then it's just from a list. So if I were to do like .random.seed1, then print a number, then do the same seed and print another number, it will be the same number. So it's actually called pseudo-random. And this is basically just initializing the seed for random numbers. And in the line below, the synaptic weights. A synaptic weight is essentially the same as the weights here. The reason why it's called synaptic is because that's just a term for it for neural networks when you're connecting for the weights between a neural network as it represents the strength between the nodes. And the reason why it's called synaptic is kind of like if you know your biology, there are like synapses that go through like your brain and your neurons, and that's basically where it comes from. So these are essentially our weights, and we want to use random weights. As you notice, right, we have our weights equal to a bunch of random stuff. The numbers here just represent a 3x1 matrix. So basically, initialize weights in a 3x1 matrix. And a matrix is essentially a two-dimensional array. And what this means is you're creating a matrix, which is essentially a two-dimensional array. And it has values from -1 to 1 and a mean of 0. And those are the initial weights we're going to start off with. And the reason why we want them to be random is because we want to resemble a real training scenario or a real life scenario. If we actually have an AI or a machine learning model that wants to classify something, it's not going to be extremely smart in the beginning. Instead, it's like not going to really know what it's doing, which is why we want to give its weights completely random numbers. So at the beginning, it will have pretty much no idea what it's doing because the weights are random. And then as we train it, we will update these weights and make them better and better using our sigmoid function to ultimately create an actual proper working program. And then the sigmoid function, this is the next function call we're gonna have. I can't explain it too in depth, but it's a logistic function that it's like a smashing function because it takes all your values and it ranges them from -1 to 1. There's some really cool articles about it, but essentially this is what it looks like. It can go from 0 to 1 or -1 to 1. In our case, we're going to do it from 0 to 1. And you can see how it looks. It's very unique because it's S-shaped. And with S-shape, it means that it's always increasing. The values are always increasing. And no matter what number you give to it, it will always max out at 1 or minimize out at 0, which is useful. And that's essentially what our sigmoid function is. And what it can do is here. So let's say we have to classify two different objects. If it's linear, it's very simple. You just can draw a straight linear line, right? Y equals mx plus b. It's simple. If it's nonlinear, something like this, now this is where our sigmoid function comes into play because it's able to kind of draw out some curves and even this is a bit unrealistic, but it's just an example, right? It's not actually going to do that in real life. It won't actually, this little point will not happen. But it's able to draw some more advanced like curve features instead of just linear lines. And that's the use of our sigmoid function. We'll link the articles later. But that's our sigmoid. And we also use the derivative of the sigmoid. And just ignore this part because it's a bit complicated. But what you need to know is it works in conjunction with the sigmoid function. And both of these together work towards creating better weights. So they're trying to constantly update these weight values that initially were random to get them to be as good as possible, which is our goal. And the next function is going to be our training function. So this is when it's in the training stage. We're going to take in a couple variables or parameters, training inputs, training outputs, and training iterations. Training inputs is pretty self-explanatory. That's the data that we're getting inputted. Training outputs is the input data that was outputted. So essentially, if I have input data of 1, 2, 3, and my output data was 4, that would be one set. And if I have another set which input data was 2, 3, 4, and output was 5, then so on, like 3, 4, 5. But normally in our case, our output is going to be between 0 and 1, and our training input is going to be between 0 and 1 as well. It'll make sense later. And so during the training stage, we want to iterate however many times this is. So for I in range of training iterations, basically if training iterations is 10, it's going to loop it 10 times. And inside the loop, we're going to call another function which has not been created yet. It's called self.think. We'll explain that very soon. And so this part, we take the training outputs, which is the correct answer, and we compare it to our answer. Output is what our machine thinks it is, and the training output is what the actual answer is. So therefore, the difference is equal to the error, right? That kind of makes sense. And then using the error, we want to create some adjustments. np.dot, this is numpy. Dot is used for multiplying matrices, or basically it's for multiplying arrays, or in our case right here, it's for updating our weights. This is what we're doing right now, updating our weights. So just ignore this part. The dot t is used to make the matrix a one-dimensional matrix. And we use the sigmoid derivative here, but that's not important. So basically, update weights with our sigmoid function via the error. Okay. And then these two lines should go together. This is the final line to update the weights. So we take our adjustments, then we add them or subtract them, depending if they're negative or positive, to the weights, so they get updated. And that's pretty much it. That's the whole entire train function. It's not that crazy, except for the math part. The math part is a bit difficult, but we don't have to understand all of it. We just need to know kind of what it does. And then the last function that didn't explain yet was a think function. And the think function, that's where, right, the machine kind of thinks and it does it by itself. So this time you don't give it any training values, you don't give it any output values, you just give it some input values. And hopefully given these input values, it's going to be able to give you the correct output value. So first we have to input them as floats. That's just because of the way this neural network is set up. We're just taking in floats or decimal numbers. Sorry, decimal numbers. So this part's not that important. And here we use the sigmoid function. And essentially, because we don't have any hidden layers within our neural network, it's quite simple for our machine. All I need to do is just multiply two matrices together and put it into the sigmoid function. And that gives us our output, which is a value between 0 and 1. And here we just return the output, which goes all the way in here during the training stage. So that's pretty much it for our neural network class. If you have any questions about any of this, now would be the time. I know a lot of parts was confusing, and it probably didn't help when I kept saying it was not that hard. But just try to ignore most of the math portions and just understand what exactly each function is supposed to accomplish, and it'll make a bit more sense. And now this is our main function where we're actually going to run and test and train our neural network. So first things first, we want to initialize it. So we create a new initialize from our class. It's not that important. And then we're going to send in a print statement saying start. So just to tell us that, we're kind of starting our program. And we'll also print the initial synaptic weights. So this part, it prints initial random weights. So that's like the random weights. And then now let's create some of our training data. So we're just gonna use a really simple example because our neural network, frankly, is kind of weak and it's not gonna be able to handle anything too advanced at all. Like, it's not gonna be able to handle anything advanced. Honestly, can't even handle the really simple problems. But it's a good structure, if that makes sense. So here is a two-dimensional array, or it's going to become a matrix. And these are some training values. Essentially, this is our input, and then our algorithm, or like formula, is essentially whatever the very first digit is going to be the output, if that makes sense. So here's our output array, and this one is just one-dimensional because there's no like set of data. Each of these three numbers are one piece of data together. So these three numbers make up one piece of data. And our output is 0, 1, 1, 0, because in case 1, we have 0, 0, 1. The first digit is a 0, so the output is 0. Second scenario, we have 1, 1, 1, output is 1, because the first digit is 1. Third scenario, we have 1, 0, 1, the output is 1 because the first digit is 1. And fourth scenario, we have 0, 1, 1, the output is 0 because the first digit is 0. And so it's like very simple. But you'll see that our machine is not like able to predict it perfectly sometimes. So that's our training input and output. And so now our next step is actually to train the machine. So we can use our .train function. And if we remember, we need to pass in training inputs, training outputs, and training iterations. So conveniently, we have just created the two arrays or matrices for our training input and output. Then training iterations, we can just give it a number. Let's just say 100. 100 is a decent number, I think. We'll let it run 100 times and keep on adjusting itself 100 times. That's a lot. And we can tweak with this number to show how our output, or like our end result, is going to be different depending on how many times we train it. So finished training, just like a little print statement. And then we can print our updated weights. So we can see, what our weights became after the training. So they should hopefully be kind of different from these. I'll add a comment, print updated final weights. Ideally, they are perfect. And then we're almost done. Now it's actually time to test the neural network. So user input 1 is going to be equal to, we're going to ask the user to input a number, basically. Enter a number, because we want to recreate one of these examples. So we're going to ask the user to enter 3 of these numbers, and then our machine is going to predict the answer. And so I'm going to just copy this piece of code twice. Change the 1 to 2 to 3, and that's pretty much it. Then we can print, actually we don't need to print anything. Let's just first print the actual answer. So neural network dot think, and then we want to put in an array given our 1, 2, 3 numbers, because our think takes inputs, which, because we're using Numpy, it's always going to be like a matrix. Okay, and then print done. So that's pretty much it. Let's test it now. We'll see if it works. There's a decent chance it doesn't. That would be unfortunate. So Python neuronet.py, no synaptic weights. Line 40. I spell it wrong? I initialize wait. Oh, damn, forget to put an underscore. Wait, let me try that again. Okay. So we can debug. Basically, I forgot to put another underscore in the beginning for the initialization, but we fixed that, and now it has another issue. The adjustments don't match up. Training inputs, synaptic weights, dot t error times self dot segment derivative output self ends. Hold on. What's that? 3,4. Oh, I think I forgot to put a dot T here. Okay, it works. I forgot to put a dot T, which basically meant that it wasn't a proper matrix for the output format that it wanted. But that's not important. We're done now. So essentially, this is our final program. It prints out start. These are the initial weights from our random seed. Then it trains, it runs it 100 times, it finishes training. These are our new weights. So you notice that they've changed drastically. Oh, they went past 1 and -1. I think I might have misspoke earlier. And so now enter a number. So we can try, let's just try 1, 0, 0. And you see that it's pretty confident that the output should be 0.99, which is pretty close to 1, which is the answer. So that's pretty good. We can try like 1. What did I try? I did 1, 0, 0. Okay, let's try 1, 1, 1, 0. It's decently confident that it's 98%, but we've only run it 100 times. So if we actually run it like a bit more, maybe like 30,000 times, it should increase a bit the probability. So see, it took a tiny bit longer, really not that much longer actually. And so if we do 1, 0, 0, we get 9999, right? And then earlier, what we got was 9902. So it is much more confident, 99% to 99.99%. That is a decent difference. And then 110, let's try that. 110 is now 1, 2, 3, 4 digits, 9999 again, when in comparison it was 98%. So that kind of shows how the more you train your model, the more accurate it will be. But then at the same time, our model's not exactly the best either, because if we try, let's say 0, 0, 0, you notice it gives us 0.5, which is kind of off because we want it to output 0, right? And so it does have its own flaws. Mainly because it's lacking hidden layers, but there's not much we can do about it. 0, 1, 0 gives 0.44, which is a tiny bit better, but let's up it one more time to 300,000, which this one should take a while. And I'll try 0, 1, 0 again. So 0, 1, 0. And you'll see it doesn't really improve. It went from what was it earlier? 448 to 449, which is actually backwards, right? We want it to be going more towards 0 instead of 1. And so that's kind of a flaw with what we currently have. But that's just because our neural network is very simple. Like in actual practice and in the real like production environment, there would be no such thing as a 61 line neural network that actually works and can classify your whatever you're trying to classify. But it's kind of a good example of how exactly this sort of thing works. And there's a couple more things that I wanted to show. So you notice that there's really not much. Oh wait, so first thing I want to show is the random seeding, right? So what I meant about the pseudo randomness was this seed is always going to give the same values. So you see in the beginning, it's always negative 0.16, 0.14, 0.44, negative 0.99. It's always the same three values because the random seed is the same. But if we switch up the random seed to, let's say 2, for example, then you notice that the three numbers are much different. And then after it trains, our weights, give it time. Our weights are somewhat similar. You notice that, let's compare. So 13.113, 13.113, negative 0.203, negative 6.355. So after training, even though the three initial weights we had, so this one was negative 0.6, this one was negative 0.2, they end up at the same value because our sigmoid function doesn't care what the initial values were. Because it's been able to run 300,000 times, it's done it enough times, trained it enough times to pinpoint it down to what it believes is the correct answer, which unfortunately is not perfect, but it still shows how the machine learning training function kind of works, which is pretty important. And there's some more advanced examples that we don't really have time for, unfortunately. But that's pretty much it for today. If anyone has any questions, now's the time. Otherwise, as a reminder, we're not gonna have a meeting on 3/17 in 2 weeks because of state testing.